Hello and welcome again to April's biomedical course. Today we are going to learn how to count cells using the haemocytometer, or if you would prefer, the Neubauer chamber. Please subscribe to this channel and please give my videos a thumbs up if you like the video, and comment on whatever you like or whatever you don't like from the video, or if you want me to make other contents, please just write it in the chat. And don't forget to share this video to your friends. You might help a friend if they need it, right? And please do subscribe to this channel because, well, first things first, it will motivate me to make numerous other videos with other contents, and number two, it will very much help with my rent, so please do subscribe. So the haemocytometer is basically a counting chamber device. It's originally designed and used to count blood cells, but nowadays we don't just use this thing, this item, this tool to count blood cells. We use it for counting various lines of cells, and all of them are usually for research purposes. One type of cell that we count is bacterial and yeast cells. The example given here is from yeast cells, of course, spanning from 8 to 12 micrometers long. And basically, well, we use this information, the cell concentration number obtained from the haemocytometer, is basically when we make a growth curve. Why do we need to make a growth curve? It's basically when we want to optimize certain aspects from fermentation processes. For example, researchers usually add a substance, and we want to know whether that substance can give a positive, negative, or neutral impact. If it gives a positive impact, then of course more research would be given to that substance. If not, then no. Another advantage of using the haemocytometer is it allows us to count for spores, bacterial and fungal spores. Scientists, we collect and store our samples, right? And sometimes we would like to store our bacterial and fungal samples in the form of spores. For bacterial spores, they usually span from 0.8 to 1.2 micrometers long, while fungus spores, they have longer range of size, which is from 2 to 100 micrometers long. And this is basically for storage purposes. We would like to know how many spores do we have. And of course, the counting of red blood cells or other blood cells from blood samples. And the last one is we can use the haemocytometer to count primary cells or cell lines. In this PPT, in this video, I give the example of the Fero cell lines spanning from 15 to 20 micrometers long. Basically, we count this for cell culture purposes, be it for medical science research purposes, or when we produce vaccines. For example, when we produce the viral inactivated vaccines or viral attenuated vaccines, those two. And well, so we can see here that this is the tool, right? And if you focus right above here, the one I'm highlighting above here and over here, you can see a very faint square. That's the grid, and this is how the grid looks like under the microscope. And this grid, these lines are made by special lasers, okay? Now, okay, so each grid has 9 big cells. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now, notice that big cell number 1, 3, 7, and 9 each have 16 smaller cells, right? Because 4 to this side and 4 to this side. But big cell number 4 and 6, they have 20 cells, 20 small cells, because 4 cells spanning here to here, and this side has 5 cells. But the one in the middle, the big cell number 5, it has 25 small cells, okay? Because we have 5 cells here and 5 cells here, right? Now, if you look at here, for each smaller cells, they have 16 mini cells. Now this distinction is important actually to help us scientists to count samples when they have too many cells or not that much cells. Okay, and we will explain that later. Now, each grid has the area of 9 millimeters square. It's 3 meters long and 3 meters wide. 3 millimeters long and 3 millimeters wide. Okay, and for each big cell, it's 1 millimeter long and 1 millimeter wide. Right? Okay. Now, from the side of the haemocytometer, what I want you to pay attention is the depth of the sample. Here we can see that there's a gap, that there's a fixed gap there. And this fixed gap is made by the help of the cover glass over here and the cover glass mounting support over here. So this ensures that no matter how much samples that you put into the haemocytometer, 5, 10, 20, 30 microliters, it doesn't matter because the depth of the sample is only going to always be fixated at 0.1 millimeter depth. And this is important because we need the volume of our counting area in order to count, in order to measure the concentration of our cells per milliliter. Now, the volume of one big box, one big cell, is 1 millimeter times 1 milliliter, right? Times 0.1 milliliter. And because of that, we get 0.1 millimeter square, which is the same with 0.1 microliter. I'm sorry, that's not micrometer, that's microliter. So, there are several counting methods. The first one is if the cells within our sample is not so abundant. The other one is if the cells in our samples are too much. So the concentration of the cells within our sample is too high. But I'm not going to explain the second counting method because there's another video for that. And I've put the link in my description as well as at the end of my video, so you can visit that later. Okay, so when our cell concentration within our sample is not so high, we can either count all the cells within all the big cells, so basically we count all the cells within the grid, or we can count just 5 cells, right? So we can just count the cells within big cell number 1, 3, 5, 7, and 9. And then afterwards we can average it. And this is one important thing that I have to say, although I didn't write it in the PPT. So basically, this is the condition of a cell of the sample that has the concentration of cell that is not so abundant. So you don't see in one small cell that there are 3, 5, even 53 cells crammed in one small cell. If you have that, then that's the condition. That's the other condition where your sample has too high of cell concentration, so you don't use this counting method, you use the other one. But the thing that I want to emphasize here is that so each lab has their own rule, and the rule is this. So in my current lab, we count all the cells that are within one big cell, but we also count cells that are a little bit outside of this big cell, if and only if the cells still touch all the lines above, right, below, and left. So if we are counting 5 big cells here, so 1, 3, 5, 7, and 9, this cell over here is still counted because it still touches the left side, the left line of big cell number 3. Okay, but other labs, their rule is to count only for the cells that touch the line on the right and bottom, or right and above. Others have left bottom and left above, or it's different from lab to lab, so you have to make sure of that before counting. So this is what we do when we want to count the cells using 5 cells or 9 big cells. Okay, so we have 53, 51, 54, 52, and 50 cells in each big cells. Okay, that's a good number. Now, we also have an additional information where from our initial sample, we took 10 microliter of sample and then we add 10 microliters of tryphin blue. Tryphin blue is a dye, and the dye will color cells that are dead. So in this scenario, we are counting only the living cells, okay? Now, the addition of 10 microliter of tryphin blue to our 10 microliter sample grants us 2 microliter of mixture, and that information will be important later for the dilution factor. So what do we do first? First, add all of this number of cells together and divide the total of that number with 5. Why 5? Because we're counting only 5 big cells. If we count 9 big cells, then the dividing number will be 9. And here we have the average number of cells as 52 cells. Okay. The next one is we can count the number of cells per milliliter sample. Basically, we're counting the concentration of cells within our sample per milliliter. Okay, so this is the formula. Basically, we from the average number of cells, we times that number with 1 milliliter and divide it with 0.1 microliter. The numbers sounded, well, familiar, right? That will be explained later on. Okay, so we get the number of cells per milliliter. The concentration of our cells is 5.2 times 10 to the power of 5 cells per milliliter. If you don't want to remember, or if you don't want to memorize this formula, then just do it with logic. If we now have 52 cells within 0.1 microliter sample, right, from one big box, right? So how many cells would we have if the volume is 1000 microliters or 1 milliliters? And of course, this number, the 52 cells, jumps up over here, and what do you know? See, the formula is the same. So that's how you get the formula. So you don't really have to remember it, you just need to understand what you're doing. Now, before we concluded it, don't forget that we have this information, and this information is important because we haven't included the dilution factor. Basically, we add the dilution factor here. So all of that number, we times that with the dilution factor, and then we get the real number of our concentration. Okay, so basically the 5.2 times 10 to the power of 5 cells per milliliter, that's the concentration of cells in 20 microliter of mixture. Why is that? That's because we, in a way, we dilute our sample, right? We add 10 microliter of tryphin blue to our 10 microliter sample. So that's diluting it, right? And that's diluting it by half. Why? Because the total volume of our end mixture is 20 microliter. So our sample, 10 microliter, from the total mixture is basically half of it. And because of that, the dilution factor is the number below. So the dilution factor is 2. So we put this number, this dilution factor, in this formula, and now we get 1.04 times 10 to the power of 6 cells per milliliter. And this is the real concentration of cells in our sample, and our initial sample, undiluted sample of 10 microliters. Okay, this is the concentration of cells in the volume of 1 milliliter. And this is the same if you do it for 9 cells, okay? And that's the end for my video. If you want to know the other method, just click on the video that is presented here. Or you can just also go to the description, and I've already put the link for the other method there. And please do not forget to subscribe and to give my video a thumbs up if you like it. Comment it also on whatever materials you want me to cover, and please share it with your friend. You never know, you might help a friend. Thank you!